Hello, this is Kana, and today I'll be talking about just-in-time compilation or JIT for EmacsLisp, based on my work in progress EmacsConf Juicemacs. Juicemacs aims to explore a few things that I've been wondering about for a while. For example, what if we had better or even transparent concurrency in ELisp? Or can we have a concurrent GUI, one that does not block or is blocked by Lisp code? And finally, what can JIT compilation do for ELisp? Will it provide better performance? However, a main problem with explorations in Emacs clones is that Emacs is a whole universe, and that means to make these explorations meaningful for Emacs users, we need to cover a lot of Emacs features before we can ever begin. For example, one of the features of Emacs is that it supports a lot of encodings. Let's look at this string. It can be encoded in both Unicode and Shift-JIT, the Japanese encoding system. But currently, Unicode does not have an official mapping for this key character. So when we map from Shift-JIT to Unicode, in most programming languages, you end up with something like this. It's a replacement character. But in Emacs, it actually extends the Unicode range by threefold and uses the actual range to ruthlessly support characters like this. So if you want to support this feature, that basically rules out all string libraries with Unicode assumptions. For another, you need to support the regular expressions in Emacs, which are really irregular. For example, it supports asserting about the user cursor position, and it also uses some character tables that can be modified from Lisp code to determine case mappings. And all that makes it really hard or even impossible to use any existing regular expression libraries. Also, you need a functional garbage collector. You need threading primitives because Emacs already has some threading support. And you might want the performance of a clone to match Emacs, even with its native compilation enabled. Not to mention, you also need a GUI for an editor, and so on. So Juicemacs, building on Java and a compiler framework called Truffle, helps in getting better performance. And by choosing a language with a good GC, we can actually focus more on the challenges above. Currently, Juicemacs has implemented 3 out of at least 4 of the interpreters in Emacs, one for Lisp code, one for bytecode, and one for regular expressions, all of them JIT capable. Other than these, Emacs also has around 2,000 built-in functions in C code, and Juicemacs has around 400 of them implemented. It's not that many, but it is surprising enough to bootstrap Emacs and run the portable dumper, or pdump in short. Let's have a try. So this is the binary produced by Java native image, and it's loading all the files needed for bootstrapping. Then it dumps the memory into a file to be loaded later, giving us fast startup. As we can see here, it throws some frame errors because Juicemacs doesn't have an editor UI or functional frames yet. But otherwise, it can already run quite some Lisp code. For example, this code uses the benchmark library to measure the performance of this Fibonacci function. And we can see here the JIT engine is already kicking in and makes the execution faster. In addition to that, with a bit of workaround, Juicemacs can also run some of the ERT, or Emacs regression test suite that comes with Emacs. So yes, there are a bunch of test failures, which means we are not that compatible with Emacs and need more work. But the whole testing procedure runs fine, and it has proper stack traces, which is quite useful for debugging Juicemacs. So with that, a rather functional JIT runtime, let's now try to look into today's topic, JIT compilation for ELisp. So you probably know that Emacs has supported native compilation, or native conf in short, for some time now. It mainly uses GCC to compile Lisp code into native code ahead of time. And during runtime, Emacs loads those compiled files and gets the performance of native code. However, for example, for installed packages, we might want to compile them when we actually use them instead of ahead of time. And Emacs supports this through this native conf JIT compilation flag. What it does is, during runtime, Emacs sends a loaded file to an external Emacs worker processes, which will then compile those files asynchronously. And when the compilation is done, the current Emacs section will load the compiled code back and improve its performance on the fly. When you look at this procedure, however, it is ahead of time compilation done at runtime, and it is what current Emacs calls JIT compilation. But if you look at some other JIT engines, you'll see much more complex architectures. So take LuaJIT for an example. In addition to this red line here, which leads us from an interpreted state to a compiled native state, which is also what Emacs does, LuaJIT also supports going from a compiled state back to interpreter, and this process is called de-optimization. In contrast to its name, de-optimization here actually enables a huge categories of JIT optimizations. They are called speculation. Basically, with speculation, the compiler can use runtime statistics to speculate, to make bolder assumptions in the compiled code. And when the assumptions are invalidated, the runtime de-optimizes the code, updates statistics, and then recompile the code based on new assumptions, and that will make the code more performant. Let's look at an example. So here is a really simple function that adds 1 to the input number. But in Emacs, it is not that simple because Emacs has 3 categories of numbers. That is, fixed numbers or machine word sized integers, floating numbers, and big integers. And when we compile this, we need to handle all 3 cases. And if you analyze the code produced by Emacs, as is shown by this gray graph here, we can see that it has 2 paths. One fast path that has fast fixed number addition, and one for slow path that calls out to an external +1 function to handle floating number and big integers. Now, if we pass integers into this function, it's pretty fast because it's on the fast path. However, if we pass in a floating number, then it has to go through the slow path, doing an extra function call, which is slow. What speculation might help here is that it can have flexible fast path. When we pass a floating number into this function, which currently has only fixed numbers on the fast path, it also has to go through the slow path. But the difference is that a speculative runtime can de-optimize and recompile the code to adapt to this. And when it recompiles, it might add floating number onto the fast path, and now floating number operations are also fast. And this kind of speculation is why speculative runtime can be really fast. Let's take a look at some benchmarks. They are obtained with the ELisp benchmark library on Nelpa. The blue line here is for NativeConf, and these blue areas mean that NativeConf is slower. And likewise, green areas mean that Juicemacs is slower. At a glance, the 2 or 4 actually seems somehow on par to me. But let's take a closer look at some of them. So the first few benchmarks are the classic Fibonacci benchmarks. We know that the series is formed by adding the previous 2 numbers in the series. And looking at this expression here, Fibonacci benchmarks are quite intensive in number additions, subtractions, and function calls if you use recursors. And it is exactly why Fibonacci series is a good benchmark. And look at the results here. Wow, Emacs NativeConf executes instantaneous. It's a total defeat for Juicemacs similarly. Now if you enter benchmarks, you know that something is wrong here. We are comparing different things. So let's look under the hood and disassemble the function with this convenient Emacs command called disassemble. And these 2 lines of code is what we got. So we can already see what's going on here. Its GCC sees Fibonacci is a pure function because it returns the same value for the same argument. So GCC chooses to do the compilation compile time and inserts the final number directly into the compiled code. It is actually great because it shows that NativeConf knows about pure functions and can do all kinds of things like removing or constant folding them. And Juicemacs just does not do that. However, we are also concerned about the things we mentioned earlier. the performance of number additions or function calls. So in order to let the benchmark show some accurate things, you need to modify it a bit by simply making things non-constant. With that, Emacs gets much slower now. And again, let's look what's happening behind these numbers. Similarly, with the disassemble command, we can look into the assembly. And again, we can already see what's happening here. So Juicemacs, due to its speculation nature, supports fast path for all three kinds of numbers. However, currently, Emacs native comp does not have any fast path for the operations here like additions or subtractions or comparisons, which is exactly what Fibonacci benchmarks are measuring. Emacs at this time has to call some generic external functions for them, and this is slow. But is native comp really that slow? So I also ran the same benchmark in CommonList with SBCL, and native comp is already fast compared to untyped SBCL. It's because SBCL also emits call instructions when it comes to no type info. However, once we declare the types, SBCL is able to compile a fast path for fixed numbers, which makes its performance on par with speculative JIT engines, that is Juicemacs of course, because now both of us are now on fast path. Additionally, if you are bold enough to pass this safety 0 flag to SBCL, it will remove all those slow paths and type checks, and its performance is close to what you get with C. Well, probably we don't want safety 0 most of the time, but even then, if native comp were to get fast path for more constructs, there certainly is quite some room for performance improvement. Let's look at some more benchmarks. For example, with this inclist or increment list benchmark, Juicemacs is really slow here. Partly it comes from the cost of Java boxing integers. On the other hand, for the Emacs native comp, for this particular benchmark, it actually has fast path for all the operations, and that's why it can be so fast. And that also proves that native comp has a lot of potential for improvement. There's another benchmark here that uses advices. So EmacsLisp supports using advices to override functions by wrapping the original function and an advice function, two of them, inside a glue function. And in this benchmark, we advise the Fibonacci function to catch the first 10 entries to speed up computation. That can be seen in the speed up in the Juicemacs results. However, it seems that native comp does not yet compile glue functions, and that makes advices slower. With these benchmarks, let's discuss this big question. Should GNU Emacs adopt speculative JIT compilation? Well, the hidden question is actually, is it worth it? And my personal answer is maybe not. The first reason is that slow paths like floating numbers are actually not that frequent in Emacs. And optimizing for fast paths like fixed numbers can already get us very good performance already. And the second or main reason is that speculative JIT is very hard. Lua JIT, for example, took a genius to build. Even with the help of GCC, we need to handwrite all those fast paths or slow paths or switching logic. We need to find a way to de-optimize, which requires mapping machine registers back to interpreter stack. And also, speculation needs runtime info, which also costs us extra memory. Moreover, as is shown by some benchmarks above, there's some low-hanging fruits in native comp that might get us better performance with relatively lower effort. Compared to this, a JIT engine is a huge undertaking. But for Juicemacs, the JIT engine comes a lot cheaper because we are cheating by building on an existing compiler framework called Truffle. Truffle is a meta compiler framework, which means that it lets you write an interpreter, add required annotations, and it will automatically turn the interpreter into a JIT runtime. So for example, here is a typical bytecode interpreter. After you add the required annotations, Truffle will know that the bytecode here is constant, and it should unroll this loop here to inline all those bytecode. And then when Truffle compiles the code, you know that the first loop here does ask plus 1, and second does return. And then it will compile all that into return x plus 1, which is exactly what we would expect when compiling this pseudocode. Building on that, we can also easily implement speculation by using this transfer to interpreter blah blah function provided by Truffle. And Truffle will automatically turn that into the optimization. Now, for example, when this add function is supplied with 2 floating numbers, it will go through the slow path here, which might lead to a compiled slow path or de-optimization. And going this de-optimization way, it can then update the runtime stats. And now when the code is compiled again, Truffle will know that these compilation stats suggest that we have floating numbers. And this floating number addition branch will then be incorporated into the fast path. To put it into Java code, most operations are just as simple as this, and it supports fast paths for integers, floating numbers, and big integers. And the simplicity of this not only saves us work, but also enables Juicemacs to explore more things more rapidly. And actually, I have done some silly explorations. For example, I tried to constant fold more things. Many of us have an Emacs config that stays largely unchanged, at least during one Emacs section. And that means many of the global variables in ELisp are constant. And with speculation, we can speculate about the stable ones and try to inline them as constants. And this might improve performance, or maybe not, because we will need a full editor to get real-world data. I also tried changing const lists to be backed by some arrays, because maybe arrays are faster, I guess. But in the end, set could require some kind of indirection, and that actually makes the performance worse. And for regular expressions, I also tried ORing techniques from PCRE JIT, which is quite fast in itself, but it is unfortunately unsupported by Java Truffle runtime. So looking at these, well, explorations can fail, certainly. But with Truffle and Java, these for now are not that hard to implement, and also very often they teach us something in return, whether or not they fail. Finally, let's talk about some explorations that we might get into in the future. For the JIT engine, for example, currently I'm looking into the implementation of nativeconf to maybe reuse some of its optimizations. For the GUI, I'm very slowly working on one. If it ever completes, I have one thing I'm really looking forward to implementing. That is, inlining widgets or even other buffers directly into a buffer. Well, it's because people sometimes complain about Emacs GUI capabilities. But I personally think that supporting inlining like a whole buffer inside another buffer as a rectangle could get us very far in layout capabilities. And this approach should also be compatible with terminals. And I really want to see how this idea plays out with Juicemacs. And of course, there's Lisp concurrency. And currently, I'm thinking of a JavaScript-like, transparent, single-threaded model using Java's virtual threads. But anyway, if you are interested in JIT compilation, Truffle, or anything above, or maybe you have your own ideas, you're very welcome to reach out. Juicemacs thus needs to implement many more building functions, and any help would be very appreciated. And I promise it can be a very fun playground to learn about Emacs and do crazy things. Thank you.